Thank you also to our colleagues from Manchester for graphene. It certainly had a huge impact around the world, and I'm going to show you some of the impact it's had in some of our own projects in our Centre of Excellence. And I was in Manchester about a week ago, and I can verify that this is pretty good weather for Manchester outside. But we're back in Australia. I come from Wollongong, which is on the map. I also spent a little bit of time in Geelong, which is just down the road here. And so I'm speaking to you today in a Geelong accent, right? Because before I went to Geelong, I had a pure Belfast accent. And now listen to me, it's terrible, right? This Geelong accent, but you'll have to bear with me as we go through. So I'm going to talk to you a little bit about some of the work we're doing in the ARC Centre of Excellence for Electromaterial Science. Our partners are listed there, the partner organisations, and we have several international partners as well. And if Quincy can click on that for me. Within the centre, we've been interested for a number of years in what happens to the properties of electromaterials as we make them smaller. As we go from the macroscopic, as we find in a traditional electrochemical device such as a battery, down through to the micro domain, we uncover some interesting electrochemical properties at the microscopic. As you go down into the nano domain, 1,000 times less than the diameter of a living cell, of course we uncover quite extraordinary properties in terms of mechanical properties, electrochemical properties, and also the ability to tune biological properties. So that's been the fundamental thrust of what we've been interested in for a number of years. And then let me add to that challenge and this dimension, because now what we need to be able to do, as you'll see through the examples, is to create structures and devices that contain these nano components and try and retain some of the properties that we've uncovered down in the nano world. So I'm going to focus today on the nanocarbons, in particular on graphene. We do work on other nanostructured electromaterials, but the challenges are somewhat similar. So we're going to talk about how we might be able to use these properties in electrochemical devices and how we might be able to structure these devices to get enhanced performance, primarily for bionics today. But I will touch on some of the energy studies that have given us valuable information in designing new electrodes and new electrochemical systems for medical bionics. So what do we mean by medical bionics? Well, perhaps the most famous example is the cochlear ear implant. This beautiful piece of machinery, which consists of 22 small electrodes implanted into the cochlea of deaf people. There's a microphone which sits on the head, which picks up sound, transposes that sound into electrical impulses delivered to each of those electrodes to stimulate nerve cells so that profoundly deaf people can learn to hear. Now that device, magical as it is and successful as it has been, there is still room for improvement. The fidelity of that sound is not particularly high. For example, it's difficult or impossible to hear music with the cochlear ear implant. And so there's a need to continue to develop new electrode materials that interface better with nerve cells. We also find in other applications, and I'll just touch on a couple today to do with bone and cartilage regeneration, that there's a need to create structures with the right mechanical properties to facilitate cartilage regeneration, the right mechanical properties to facilitate bone regeneration, and with electrical properties that can help stimulate that regeneration process. And I won't talk about epilepsy detection and control today, but the challenge there is to develop highly flexible electrodes that will be implanted directly into the brain to pick up the signals warning of an impending seizure and then to deliver a counter stimulus to try to avert that seizure in epileptic patients. So here's the first story about flexible electrodes and being able to stimulate nerve cells. This was a project with Professor Rick Kanner at UCLA. And with using Rick's process, we developed a biopolymer electrode, which essentially looked at using a CVD method to grow layers of graphene on copper. Rick was using an engineering polymer to put on top of that structure after it was grown, and then etching away the copper to leave the graphene layers on the polymer substrate. So simply what we did was to replace that engineering polymer with a biopolymer, something that we knew that would be cytocompatible and eventually totally biocompatible. And we were able to create highly flexible electrode structures with just bilayer or few layer graphene deposited onto that biopolymer. And then the challenge was to see, could we actually, first of all, grow nerve cells on that electrode structure? And could we, through this perhaps thinnest of all electrode structures for electrochemical applications, still communicate with living cells, still communicate with nerve cells? So the first experiment was to be sure that we could grow nerve cells on those structures, and we found that the nerve cells grew equally on these flexible graphene structures, equally well as they did on more conventional and more standard substrates. Then the crucial experiment was to see, could we take this particular structure where we could get high proliferation of nerve cells, that's the PLA plus graphene electrode structure, grow the nerve cells and see, could we get an effect due to electrical stimulation? Could we communicate with nerve cells through these two layers of carbon? So the electrical stimulation we used is similar to the stimulation used in the cochlear ear implant, and we find that we have a look at the average cell density. We don't increase the number of cells that's in a particular area, but we do start to see that we get an effect in terms of the average length of the neurites coming from those cells. And the number of neurites and the length of those neurites is a measure of the effectiveness of communication with those individual cells on that surface. So here we're using the stimulation similar to a cochlear ear implant, using these two layers of carbon on a biopolymer, which is cytocompatible, and getting highly effective communication with those nerve cells. Of course, that approach is somewhat limited in the configurations that we're able to generate, the configurations of different devices. You can imagine from those three applications I showed you with the three clinicians that we work with, that the configuration of the devices and the structures required for each of those is somewhat different. So we have been interested in parallel then how we might be able to use chemical processes in order to generate graphene, and then to use those chemical processes to fabricate graphene-containing structures. So our chairman, let me first of all talk about the source of graphite. Obviously, for this process, we need to track down some graphite. We actually started looking around Australia. There's not much graphite in Australia, as it turns out. We seem to have everything else. But if you have a look at where graphite's distributed around the world, we don't even get a blip. Despite that, there is at least one graphite mine in Australia, which we have managed to get some samples and some other samples from around the world. And of course, we're interested then in how we can take that source of graphite and turn it into graphene and then graphene-containing structures. So having identified the source or sources of graphite, we, as other people around the world, have been interested in how you might be able to exfoliate that graphite, and there are many different approaches to getting that exfoliation process, how you might then purify it, and then, of course, having a look at having added oxygen to it during the exfoliation process, how we might be able to reduce it back to the graphene structure. And doing this all the time while thinking about, in our case, optimising electrochemical properties, but also thinking about how we're going to process those structures into useful devices. So Dan Lee, our chairman, introduced our lab and our centre to graphene a number of years ago. And this very simple yet elegant example where Dan was showing how he could exfoliate the graphite and the graphene oxide, and then control the reduction process, control the pH during the reduction process in order to get highly stable dispersions, highly stable aqueous dispersions. And some of that early work, Dan showed that we could make then graphene-containing structures using various approaches, by spray coating, layer by layer deposition, or by simple vacuum filtration. So this was the start of that journey, always thinking about how we're going to process and make these devices, make the structures that we want for bionic applications. Very early on, we did show that these graphene structures were cytocompatible, that we could grow living cells on those structures, and that their proliferation, their survival rate and their proliferation was as good on any other standard cell growth surface. Some of those early studies weren't so successful though, particularly in the energy storage area. and this was some work where we were trying to use these layered structures in a lithium-ion battery as an electrode material, where we need to insert ions in and get ions out of that structure reversibly in order to get high performance. Well, the electrochemistry was pretty revealing. The first scan showed very nice lithium intercalation and de-intercalation, and the second scan showed just about zip. And that was reflected in our early studies on the capacity. If you just look at the capacity curve there versus cycle number, extremely high capacity in that battery during the first cycle, diminishing quite rapidly on subsequent cycles. So very early on, we realized that we would need to create electrode structures where we could maintain the porosity, maintain the structure during charge injection and during charge extraction from those structures. Some of the energy studies that we looked at in order to do that were to add additional material that might help retain that structure. So we had some work where we were looking at adding carbon nanotubes to the graphene-containing electrodes, still making them by simple vacuum filtration in this case. But if we just look across the top, A, B, and C, you can see B, where we have the mixtures of carbon nanotubes and the graphene material, that we do retain this open, porous structure. And that's reflected in the electrochemical experiments that we did subsequently. Just looking at the cyclic voltammograms there, highly capacitive in nature, can store a lot of energy through double layer capacitance in that open electrode structure. And probably what's more important is the number of cycles. The number of cycles in that top curve are 10,000 cycles without any loss in efficiency of getting charge in and charge out of those electrode structures. There are other ways to lock in that open porous structure in graphene-containing electrodes. One is to partially vacuum filter and then to freeze dry the structure in order to lock in the particular open porous nature that we might want in these electrochemical devices. And again, that approach proved highly successful in terms of creating flexible electrodes. And remember, flexibility is also important for bionic applications, but also in terms of the charge storage capabilities and the ability to get ions in and out or to access the double layer capacitance in those electrode structures. There are other ways to lock in the porosity, and this particular way gets us closer to something that might be very useful as a bionic electrode. We find that if we exfoliate the graphite under very careful conditions, that you can get very large sheets of graphite. And with those very large sheets, as we increase the concentration, we can form liquid crystalline dispersions of graphite oxide. Now that in itself was quite interesting, but what was really important for us is that it opened up a lot of fabrication approaches that weren't accessible to us previously. So that exfoliation process, we can get, you can see very large sheets around about 10, 20, 30 micron during that exfoliation process. And controlling just the concentration, we can control the rheology of that solution, of that dispersion. And of course, the rheology is very important in fabrication techniques such as printing and even in wet fibre spinning. So simply controlling the concentration, controlling the viscosity, opened up new fabrication options to get to new electrode structures for bionics. So we did use wet spinning, and if Quincy just clicks on the, he's got the order, he's great. Wet spinning, very simple approach, taking those dispersions. This is actually wet spinning of a carbon nanotube fibre, exactly the same approach. And what we're doing is just injecting into a coagulation bath. In the case of graphene, that can be calcium chloride, change in ionic strength, could be a change in pH, which encourages that collapse into the fibre, or it could be another polymer binder, such as chitosan, for example, a biopolymer, which encourages that collapse into the fibre. These two approaches are very similar. What you're seeing here is just a different mechanical approach. The advantage of the long tube is that we can control the hydrodynamics for longer during the fibre spinning, and so we get a higher quality fibre. And then the schematic at the bottom shows our fully engineered approach where we're not only controlling the coagulation bath and the length of it, but actually the tension applied during the fibre take-up, so you can stretch the fibre or condition it thermally in order to get better properties. So we use this wet spinning approach and different coagulation baths in order to form these fibres. These are fibres formed with a calcium chloride coagulation bath. You can see that it retains some of that liquid crystalline structure in the fibre itself. Very mechanically robust fibre structures, very flexible, and so potentially useful for bionic applications. Depending on the coagulation bath we use, it does influence the structure of the fibre and hence the mechanical properties. So there are some of the compositions of the coagulation bath, and you can see it has a dramatic effect on the mechanical properties. Also has a dramatic effect on the degree of porosity that we can retain in those fibre structures. This is a fibre that's collapsed or coagulated from an acetone bath. We use this again for charge injection, extraction. Very stable in terms of the ability to do that over quite a number of cycles, and very high specific capacity, even at high current densities. We provided some of those fibre electrode structures recently to some collaborators at the Bionics Institute in Melbourne, and let me just show you a little bit about what they've been doing with these fibres. So in order to insulate that fibre, they use a perylene coating, which is totally biocompatible. And then to ablate the end of it, or to expose the end, they use laser ablation. That not only ablated the end, but it actually resulted in a highly porous, very high capacitance electrode at the end of that structure. So excellent mechanical properties and very good electrochemical properties in terms of capacity and in terms of cycling, the ability to get charge in and get charge out of the electrode structure. The mechanical properties are just demonstrated on the top two images there. It's a fully fabricated electrode, which we're going to use, first of all, to excite tissue and then to implant directly into the brain of a rat during these experiments. Excellent electrochemical properties in terms of capacitive nature, shown in the cyclic voltammograms, and also a nice potential window in terms of being free of electrolysis over a wide range of potentials. And as I mentioned, very high surface area electrode can be created. If you just have a look at down the bottom there, you can see that, and we just look at the charge injection capabilities. That charge injection capability is dependent on the double layer capacitance, also on the potential window that's available. And these electrodes, these fibre electrodes, are as good, if not better, than any of the previously used electrode structures for neural recording and neural stimulation. Our colleagues had a look at stimulation experiments, taking the retina from the rat and exposing then the electrodes to that retina, living cells, and using a patch clamp technique to show that we could downstream effectively stimulate those ganglion cells in the retina. So we were able to insert that electrode into that tissue without doing damage. It had the right mechanical properties to do that. And similarly for recording, it had the right mechanical properties to insert directly into the cortex of the rat and to pick up neuronal recordings from that electrode structure. So it's the combination of these mechanical properties that we can engineer, along with the electrochemical properties, that really make these graphene-based materials highly effective for bionic communications. Let me just go back to the other examples in terms of regenerative bionics. So that's what we would call electrodes for communicating with nerve cells, perhaps electrodes that will be useful for things like the cochlear ear implant or for other neural prostheses. In the area of regenerative bionics, where we're looking to regenerate damaged nerve, damaged muscle or bone and cartilage, the requirements for those structures obviously are somewhat different. For a start, we need them to degrade. We need them to have the right mechanical and electrical properties, but also the right rate of degradation so that they can disappear from that site of injury once the repair has been initiated. So in order to achieve that and to build structures like this, we've been looking at how we can create new ways of fabrication for graphene-containing biocomposites. This is just an example of what we would use for nerve repair, and I just put it here because it highlights the complexity of the structures that we need to create from these graphene-containing materials. So one way to do that and to introduce the conductivity and electrical properties that we want into the structure is to have a look at making composites with well-known biomaterials. Polycaprolactone, for example, is well known as a material that can be built into three-dimensional scaffolds and is highly effective for supporting bone regeneration. So we were interested in could we develop new chemistries in order to create conductivity and electrochemical activity out of those polycaprolactone-based structures. We found that simple mixing of the graphene with the polycaprolactone was not highly effective, that we got too much phase segregation during the casting or other fabrication processes we might need to use. So covalently linking small chains of polycaprolactone to the graphene prior to the mixing resulted in highly effective dispersion throughout the structures. We did have effects on the mechanical properties, as we would expect, increasing the modulus and decreasing the elongation at break. So we were able to effectively distribute the graphene sheets through covalently linking throughout the structures. Conductivities of about 0.01 Siemens per centimetre were certainly sufficient for the applications that we had in mind. We also found that these materials did degrade, as we would expect, but the addition of the graphene does have some impact on that degradation process, and in fact provides a route to not only providing control over the mechanical properties, but some control over the degradation profile that we get, and that's important for certain applications. Also found them to be highly cytocompatible. A range of cells and cell lines grew effectively on these new biocomposites. And highly processable. Polycaprolactone can be 3D printed. That's what's often used to create the scaffolds to support bone regeneration. And we found that the polycaprolactone containing the graphene was also highly printable using the fused deposition modelling method with pretty good resolution down to about 100 micron feature size. And does it degrade? Well, I've already mentioned that it does degrade, but let me just show that also we can control that degradation process. If you just have a look here, the bottom curve, that's the covalently linked 5% graphene in that biocomposite, and we get a much better rate of degradation, a much more uniform rate of degradation compared to either the bare material or the composite structure that we're interested in. And importantly, let me skip that, importantly, we find that the products from that degradation are not cytotoxic, that we can take those products from the degradation and they won't damage the proliferation of living cells. We show one other biocomposite. It's 3D printed chitosan. So we've been using 3D printed chitosan for cartilage regeneration. This procedure involves taking the scaffold, injecting adipose stem cells, they're fat stem cells, into that 3D structure. We find that if we get the structure just right, and a lot of that has to do with controlling the modulus again of the structure, we can get highly effective generation of cartilage from adipose stem cells, from fat stem cells. The big challenge here is in how we match that cartilage and integrate the cartilage in bone regeneration at that interface. That requires the ability to control the modulus throughout the structure, and also we would like the ability to use electrical stimulation to facilitate bone regrowth. So again, we set about developing chemistries that would enable us to take the chitosan and introduce graphene, this time using lactic acid as a common solvent that enables us to do that. We find that we can maintain a lot of the properties of the chitosan structures after we add the graphene, that they still do swell, but the degree of swelling is dependent on the amount of graphene that we put into the structure. And of course, the mechanical properties are also influenced by the addition of graphene, as is the electrical conductivity. Now this, of course, is exactly what we want. This is exactly the new dimension we want, a means to control modulus, to control the stiffness as well as to introduce electrical conductivity into those structures. And always, again, with an eye to the processability. And so, again, we find a simple solution. We can use extrusion printing, 3D printing, in order to build up those scaffolds. And so now we're at the stage of looking at integrated structures that go from just chitosan through to the chitosan containing graphene, a gradient structure which we hope will facilitate this bone cartilage, the generation of this bone cartilage interface. And you can see if you use confocal microscopy that you can grow cells throughout that structure. You can drill right through that structure and see if we get even cell growth throughout this new bionic material. So we're still left with a few challenges, and let me finish with these. We can create these structures. We can create materials containing graphene. We can get electrodes based on the fibres, which are very good and effective at direct neuronal communication. We can build the biocomposites that are cytocompatible. We can control the degradability. We can control the electrical conductivity and the mechanical properties. But in some cases, the electrical conductivity is not as high as we would like it to be for some applications. So we continue to strive in parallel to build new protocols and new machinery that can help us to create new structures that contain graphene. I didn't mention where we were, did I? Yeah, I told you we're in Wollongong. But this is the innovation campus in Wollongong where we're located, just right next to the beach there. So if you want to come and visit us, please do. Because if you get bored talking to us, you can just go and have a coffee and enjoy yourself at the beach. It's a brilliant location. And within there, we've been able to build up, as well as the fundamental chemistries we're interested in, build up facilities and expertise that enable us to look at new ways of fabrication. So, for example, let me just give you a few examples in closing. We've been able to take those fibres that we're able to create. These are actually polyurethane graphene fibre composites that we've created by wet spinning. And using perhaps the oldest approach to 3D fabrication, knitting or braiding, we're able to build up very complex structures. You can imagine taking different fibres here of different biomaterials, some biomaterials to help facilitate and provide structure, so say nerve or muscle growth and regeneration, and other fibres to do the electrical stimulation, and maybe other fibres containing growth factors or other protein molecules within that structure. So the whole area of using fibres in a smart way to build up three-dimensional structures really opens up a lot of possibilities for new bionic devices. I've mentioned that we can spin fibres out of those liquid crystalline geodispersions. We can similarly use 3D printing to build up 3D structures containing that LCGO. And we've been developing ways to print coaxially. So this would enable us, for example, to print a solid graphene core inside a biopolymer. And that biopolymer, we've developed techniques to enable us to print stem cells, for example, and that biopolymer can contain those stem cells with the graphene core providing a means for direct communication with the stem cells. I haven't mentioned this before, but we've also found that with stem cells and electrical stimulation, that the degree of electrical stimulation and the type of electrical stimulation can determine the fate of those stem cells, determining whether we go to neuronal cells, for example, or glial cells. So the ability to build very complex structures requires the ability to continue to evolve the machinery to do so. And this particular printer actually is an interesting structure itself, because the printing head on this and all of the other components for it were actually created using conventional 3D printing. So using conventional 3D metal printing to create the coaxial head, and using conventional 3D polymer printing to create the other componentry required for those structures. And similarly, that's true for this other coaxial printing device, which allows us to take preformed graphene fibre and now print the polymer around a preformed fibre which is drawn during the actual printing process. So the journey has certainly been one from materials design and discovery, always thinking about how we might create the properties we want in terms of electrochemical and mechanical and biological properties, but being able to create those properties in a way where the process or the material is still processable and we can create practical, fabricatable structures. So I think our journey has just begun in terms of creating new structures, new bionic structures containing graphene. What we've tried to show today is that we can use the CVD deposition method to create those highly flexible electrodes, that we can use the chemical processing method in order to create chemically different structures and devices, some of that requiring, after the reduction process, the ability to attach other polymer chains to the structure, because that assists in the fabrication and also in the properties that we want. We've also had a brief look at how we can control the size of these structures. Attaching these polymer chains will be important after we control the size, because there we can create the biocomposites that I've described to you in terms of the chitosan and also the polycaprolactone. And it opens up the means to fabricate, to 3D print, and in some cases even to inkjet print those structures with very high resolution. And then finally, we just touched on how we can again control the size of the sheets, but this time using careful conditions during the exfoliation to control the size of those sheets so that we can form liquid crystalline dispersions. And those dispersions are really open up a lot of opportunities in terms of fabrication, whether that's for 3D printing or for the fibre spinning, as we spoke about just before. It's great to be at this event. I love coming to these events because it opens up so many opportunities to build new collaborative activities. You can imagine that in developing new devices and new materials for medical bionics, it can't be done in isolation. We work with material scientists, biologists, and my clinical colleagues here who all drive each of these projects. These are guys with real patients, real needs, who need real devices in order to tackle the types of challenges that I've described to you today. Now, of course, we also build collaborations as we do at events like this around the world, and those collaborations are critical to success. I mentioned just a couple today, one with Rick Kenner at UCLA. I should have also mentioned the work we're doing on neuronal recording with Mario Romero-Ortego at University of Texas in Dallas. And I will finish with a sincere invitation that if you're in the Wollongong area around Sydney, please do come and visit us. We'd be excited to have you, and I'm sure that you would enjoy talking to my colleagues, seeing the facilities that we have that enable us to tackle these big challenges in creating graphene-containing structures for medical bionics. Thank you for your attention.